It is my pleasure to present our team solution as top 5 teams at OCRTOC. My name is Yiting Chen, and I'm currently an undergraduate student from Wuhan University. First, I will briefly introduce our team. Then I will present our team solution pipeline. In the last, I will make a conclusion of our solution and discuss our solution's drawbacks. There are totally 6 members in our team, under the supervision of Professor Yasmin Bakiagul and Professor Miao Li. You can easily tell from our team's name that our team affiliates to Wuhan University and Chalmers University of Technology. This flowchart shows our solutions pipeline. The Kinect camera is responsible for objects location, and the RealSense camera is responsible for grasp pose generation. Each rectangle represents a rows node running independently. Task Planner node will call object location node and grasp pose generation node to get required response, and control Panda arm to execute table organization task through our robot control framework. First, let me introduce our object location node, which is based on mask RCN doing the instance segmentation. At this step, we will have the object level and pixel level detection information. The segmentation neural network performs really good in simulation. From our experiment, we have not met any misdetection. Even with some cluttered scene, the mask RCN can segment objects really precisely. Based on the pixel level segmentation mask, we can easily segment each object's depth information provided by Kinect camera. For each object's depth information, we translate them from pixel coordinate to word coordinate, and use the center of the bounding box to present their position. At this step, we can also use ICP to further detect each object's 6D pose, but we find it not that necessary to do it. As long as we can obtain the depth information from our target object, we can actually able to grasp our target object without knowing its orientation. We can directly generate grasp pose from depth image using deep learning methods. So this node will only provide each object's category and 3D position information. Now let us focus on the grasp pose generation node. Based on position information provided by object location node, we first move the RealSense camera right above our target object. There will certainly have other objects captured by RealSense, so we use dbScan algorithm, a density-based point cloud clustering method to segment our target object. After we cluster every point based on density, we assume the point cluster closest to the center of the field of view is our target object. After we remove other objects from our site, we run ggCNN to generate our 2D planar grasp pose for target object. In order to train our neural networks, we have to collect enough high-quality data to feed them. For instance segmentation, we generate more than 6,000 well-labeled images, and for grasp pose generation, we manually labeled more than 100 depth pictures. Our data are all generated based on the variation of the open tasks provided by OCRTOC official. So I assume there will be bias that hinder our solution's performance when our neural networks facing those hidden tasks. Our object location node and the grasp generation node cannot function without our task planner. And our task planner must depend on our robot control framework to execute the organization task. The left rectangle introduced our task planner logic. First, we sort our task list by moving distance of each object, and then we adjust the task list by stacking situations. A stacking situation occurs if one object is placed on top of another. We make sure that we will always pick the upper object before bottom object at initial scene, and do our best to pick the bottom object before upper object at target scene. Here shows the pipeline of our task planner. And this GIF shows the output of our task planner. We did not involve consideration about complex trajectory planning, so we totally abandoned MOVEit and write our own control framework based on track IK. We set constraints on joint positions variation to ensure the smooth trajectory of Panda, and use previous joint position as C to get the numerical solution. Here the GIF shows our control framework's function. Here is the whole pipeline of our closed-loop execution of table organization task. First, we will call the object location node to have an initial position list, and then we will pick and place each object according to the task list output by task planner. After we iterate the whole list, we check if the error of each object is acceptable. If yes, the task ends. If not, we run our task again on those objects with large error. Here is the short GIF shows how our system works. In conclusion, we provide a clear and robust robotic system structure for table organization robot. Our system consists of 3 independent nodes. Each of them is in charge to communicate with one hardware device. We only tested our solution within PyBullet, and our solution performs the best among all PyBullet teams. I'm always curious about how our score will change if we switch our solution based on CPM. We had a lot of struggle with the collision simulation provided by PyBullet. In some situations, the gripper might just stick into our target object, and the object and gripper will be together forever. This situation will ruin our whole task and brings catastrophic effect on our task score. And also, even slight collision might lead to huge impact on object in PyBullet simulator, which badly hurt our task performance. This GIF shows that the box just flew out of the desktop after a slight collision with Panda gripper. Situations like this happens a lot. Our solution is still far from an ideal table organization task. We did not consider the collision situation happens very often, and our pipeline might grasp the wrong object when stacking situation happens in front of real things. The task planner is also not considerable enough to deal with complex stacking situations. In the future, I think we need to put more focus on the precise 60 post during the whole manipulation process. For now, we only pay attention to the 3D position of objects, which is not enough for tasks with precise post requirements. Simulation will never be our final goal. How to properly transfer our system from simulation to reality will always worth our research. Thanks for listening. Please feel free to raise any discussions or just email me for more details.